What's up, you Pirate Physics geniuses? I've gotten a few questions about the lesson over work, so I thought I would send you one from home. That would be the best way to do it. I got on my pirate gear today, representing the high, and what good physics teacher doesn't have a whiteboard at home? So let's get rolling. I'll be using the notes from the first PowerPoint that I linked in my website, so if you want to pull that up, and pause the video and we'll go through those. So it should say Chapter 5, Work and Energy. So the first question is this. From physical science in 8th grade, I know you probably talked about work, you should have. So what does it mean if you do work? Think about that. No, it doesn't mean you go to a job and get money. I'm talking about the science definition of work. If I push on this cabinet right here with a great force, and I just happen to build these cabinets so I know they're pretty sturdy, I can push on this and push on this and push on this until I'm out of energy. Did I do any work? That's the question. And the answer is no. I did not move this cabinet, so therefore I did zero work on that cabinet. If I were to take my coffee cup here, I don't know if you can see it in the frame, but if I move that coffee cup 1 millimeter, I did more work on that coffee cup than I did pushing on this all day long. So there's two requirements for work to be done. First requirement is it requires a force, and we already did a whole chapter on forces, and it requires displacement to occur. So looking at the first slide in your notes, it should say the definition of work. The definition of work states this, that the work done by a constant force acting on an object is equal to the product of the magnitudes of the displacement and the component of the force parallel to that displacement. That's kind of wordy, I know, but it basically says this: in order for work to be done, take the force and the displacement and multiply them together. So the formula for work is equal to force times displacement. So I'll write that on the board, that work, and I'll do it big because I know you might not be able to see this board real well, but work is equal to force times displacement. However, there's a catch. In order for work to be done, and the wordy definition states this, but let me put it in my own words, the force has to be parallel to the displacement. That means if you're pushing something that way and the displacement is that way, you did work. If you push it that way and the displacement is that way, you did work. So let me give you an example. Here's a book. I pick up this book from here to here. Did I do work on the book? Yes, I did. I applied a force that way. I lifted it that way. The displacement was that way, so I did work. What about if I dropped the book? Did gravity do work on the book? Yes, it did. Gravity's force is that way. The displacement of the book is that way, so gravity did work on the book. How about this example? Did I do work on the book then? No, because I'm still holding up on the book, but the displacement was in that direction. So if my force is this way and the displacement's that way, I did no work on the book. Now, did I move? Yes. Were my feet doing work on the floor? Probably so. Was friction doing work against me? Probably so. But as far as the book goes, if the book was the free body that you drew, I lifted up on the book, but the displacement is that way. Last time I checked in math, that's called perpendicular, not parallel. So in order for work to be done on an object, the force and the displacement have to be parallel. Here's a good example, friction. Think about friction for a second. Does friction do work on objects? If you answered yes, you know what I'm going to ask. 3 letters. Why? Why does friction do work on objects? I'll give you a second to think about that. Got an answer? Well, here's the answer. If an object is moving that way, which way is friction? Opposing the motion. So are those two parallel to each other? Is the displacement and the force parallel to each other? Yes, they are. What about if an object was going upward, which way is air resistance, also known as fluid friction, in the opposite direction? Is friction doing work? Yes, it is. What about if the object's going that way? Which way is friction acting on? Well, that would be in that direction. So friction is a good example of something that always does work because it always acts parallel to the motion of the object in the opposite direction. So the force and the displacement don't have to be in the same direction. They just have to be at least parallel to each other in order to do work. Now, what if I were pulling on something at an angle? We did two-dimensional forces. For example, let's say you walked your dog and you have a really, really, really big dog like this. And I know my artistic abilities are not that great, but we'll pretend this is a really, really, really mean big dog, something like that. There's some whiskers right there. And you're pulling on a leash in that direction, but the dog's displacement is forward, of course. He's not walking backwards, he's walking forward. From your frame of reference, are you doing work on the dog if you're pulling that way? Well, yes, you are, but is all of your force, all of your applied force, or the tensional force in the leash, if that's what we want to call it, is all of that force doing the work? No, only the horizontal component of it is. Only the X component of that force. So if you knew the angle of that leash, whatever that angle is, theta, and you knew we'll call it the hypotenuse or the resultant force, couldn't you use your trig functions to find that horizontal component? Couldn't you say the cosine of theta times the actual force would give you this horizontal side? So that horizontal side, which is pulling backwards, is the only one that's doing work. The vertical component has nothing to do with doing work in the forward direction. That force will never do work if something's moving forward. Now, it may play a role in the friction if we get to that later on in this unit with another video maybe, but we won't worry about that yet. So there may be times where you need to resolve a force into components to find the component that is parallel to the displacement. And that's what your notes say. It was kind of wordy, like I said, but I told you I'd explain it. It says it's equal to the product of the magnitudes of the displacement. So there's my displacement, and the component of the force parallel to that displacement. If it's the whole force, well, you just use that one and multiply it to displacement. But if it's two-dimensional, you may have to resolve it and find that component. Now, here's the other question. From the dog's frame of reference, is the dog doing work on you? Well, yes, it is, because the dog is pulling forward on you, and his displacement's forward, and those are parallel to each other. So the dog is also doing work on you. So you're doing negative work on the dog, trying to slow him down, at least the horizontal component is, and the dog is pulling forward, doing work on you. Hopefully I said that right. I think I did. But anyway, let's go to the next slide and see what it looks like. There's a couple examples. There's a guy pushing on a box or a crate, and this other guy chilling, drinking his coffee. Might be a good time to have a sip of coffee. Is that guy doing any work on that crate? Well, no, he's not, because if he's not moving the crate, it says displacement equals 0. He's not doing any work on the crate. What about the skier? He's being pulled in the forward direction by force, and his displacement is forward, and those two are parallel, so obviously work is being done. And then the girl mowing the lawn, obviously a lawnmower moves horizontally, but when you mow the lawn with a push lawnmower, you don't get down like this and push on the handle like this, completely horizontal. You actually push downward and forward. remember that free body diagram we did of the little poppy toy? How you push downward and forward on the handle to move it forward? Well, that's what you would do on a lawnmower. Well, the downward component of that has nothing to do with moving a lawnmower forward. It's only the forward component that does the work. So that's a good example where you'd have to resolve that, that component of the force and make it parallel to the displacement. Multiply them boys up and you got some work. Now work, if you're multiplying, the next slide says it gives you, by the way, I don't like that F cosine theta because I've already explained that, and you know how to do this. If you know how to resolve, which you do already, just find the side that's parallel to the displacement. And there you go. It would be F cosine theta. The hypotenuse times the cosine of theta would give you that side. But anyway, so I just use this formula. Work is equal to force that's parallel, there's my little parallel symbol, times displacement. If you're multiplying force in newtons times displacement in meters, you get what's called a Newton meter. Well, the other way of stating a Newton meter is, you probably can't see this. I need to go get some dry erase markers before I do this again. That's called a joule. So the unit for work is a joule. So you got force in newtons, displacement in meters, and a Newton meter, also known as a joule. So the unit for work is a joule. So when you see a problem and it says, I think number 2, the very first problem you were supposed to do was 1 times 10 to the second megajoules. That would be 1 times 10 to the second, that would be 100 megajoules. Well, a megajoule, what's a megajoule? That's a million joules. So that would be 100 megajoules, or 100, did I say that right? Yeah, 100 megajoules, and a megajoule is a million, so that'd be 100 million joules. So, sorry there, who was that? Yeah, that was Abby. Both Abbies were working on that problem, and I told them the wrong conversion there, and they got it wrong when they emailed it to me. But so that in number 2, that first problem would be 100 million joules, 100 megajoules. But anyway, moving on. Let me go back. Work does have a sign to it. The confusing thing is, hopefully you don't get confused about this, is that work can be positive or negative, but it's not a vector quantity. It does not imply direction. So it's pretty easy though. If the force and the displacement are in the same direction, then that's called positive work. So you could be pushing something that way and the displacement's that way, and that would be positive work. Or you could push something that way and move it that way, displacement, and that would be positive work. So neither one of those tell you which direction it's being pushed. It just tells you that the force and the displacement are in the same direction. For example, the gravity example that I just used on this book, as you lower this, as this book falls, gravity is doing positive work on the book. Gravity's force is downward. The displacement is downward. That's positive work. As I lift this book, I'm lifting it with a force upward. The displacement is upward. So I did positive work on the book. What about when I lower it? What kind of work is done on the book when I lower it? It's not positive work. I'm not pushing down on the book. I'm not doing this. Okay, get down, book. I'm still lifting up on the book. I'm still holding up on the book, but the displacement is downward. So if same direction is positive work, then opposite directions must be negative work. And that's true. So that's what this next slide says in your notes. It says, if the force or a component is in the direction of the motion, the work done is positive. For example, in lowering the book, I'm still holding up on it with a force, but the displacement is downward. I'm actually doing negative work on the book as it lowers. Now, once again, what's gravity doing on the book as it lowers? That's right. It's doing positive work. So gravity's force is downward, the displacement's downward. So I'm doing negative work on the book, gravity's doing positive work on the book as it lowers. And then it says if a force or a component of the force is opposite the direction of the motion, the work done is negative. So work does have signs. So if you get a negative answer for a problem, it doesn't mean it's wrong. And if you get a positive answer for an answer, it doesn't mean it's right. It could have been a negative. Should have been a negative answer. It means you had a sign problem somewhere when you were working it. So here's a good thought question. What kind of work does friction do on objects? That's right, negative work. Friction always does negative work. Why? Because it always opposes motion. So if the object's moving that way, friction's that way, negative work. If it's moving that way, friction that way, negative work. In fact, if it weren't for friction, we talked about last week or week before, whenever that was, my days are getting off here, that if it weren't for friction, you wouldn't move. Your foot wants to go that way when you push off on the floor, so friction is opposite that way. So friction actually does negative work on your foot to help you move forward. Now, don't confuse that. Friction is not what's pushing you forward. The floor, the reaction force of the floor, Newton's third law for the reaction is equal to the reaction. The floor is actually pushing you forward. Your foot's friction is just sticking your foot in place to help you push off, or help the floor push off. You actually push on the floor, and the floor pushes you forward. So without friction, we wouldn't be walking, or we wouldn't be changing direction. We wouldn't be speeding up, slowing down. And that, boys and girls, is why physics is in everything. That's why it's so important, because everything you do involves physics. So hopefully now, maybe those problems will make a little more sense to you when you try to work them out, that you're looking for the force or a component of the force that's parallel to the displacement, or if it gives you the work in the problem and the displacement, well, work divided by displacement should give you the force causing that, or work divided by force, by displacement should give you the force. I think I said that right. But the last thing is, there's a term known as net work. Well, we've talked about the term net over and over and over again. Net means you have something left over. So in order to find the net work, well, what are you going to do? Well, take all the forces and add them boys up. So if they add up to something other than 0, then you have a net force. So I think it's problem number 8 on your problems you're supposed to do. There's something going down a hill. It might be a cannonball, or it might be something going down a hill. So you need to draw your free body, the cannonball, going down the hill. Find the components of that weight of that cannonball. And remember, it's only the x component of the weight that pulls it down the hill. So you're going to have to resolve that. So if the displacement down the hill is this way, then only the x component of the weight is what's doing work to pull it down the hill, parallel to the displacement. So that's what's doing positive work on the cannonball. So displacement that way, force that way, the x component of gravity that way, that's positive work, but it also gives you mu in the problem. Remember, mu is the coefficient of friction. I think it was 0.13 was the coefficient of friction. So don't forget to put friction in that problem. If you take the normal force, which would be equal to the y component of gravity, those two are balanced because there's no motion in the y direction. So if you know the y component of gravity, you know the normal force, and if you multiply the normal force times mu, that gives you friction. Hopefully you have that formula on your formula card or somewhere you remember it. Frictional force is mu times the normal force. So now you have a net force acting on that object. You have gravity's x component pulling it down the hill. You have friction going it against it. So the sum of those two, the positive x component minus the frictional force, gives you the net force acting on that object. And when you multiply net force times the displacement, however long the hill was, I can't remember, 18 meters or something like that. I can't remember, 12 meters, one of those two. then that would give you the net work on that object. So when you see a problem that says, I need to know the net work on an object, that means there's probably more than one force acting on it. You need to find the magnitudes and the directions of those forces and add them boys up and multiply it times the displacement, and that would give you net work. Number 10 on that handout is written kind of weird. It's pulling a chandelier across a horizontal surface, and it says the ropes are parallel to the surface. So basically it means this. They're pulling the chandelier forward, and the ropes look like, I don't know if I can do it, the ropes look like this at 45-degree angles, except they're parallel to the floor. So really all you have to do is find the component of that force on the tensions in the ropes. If it's a 45-degree angle, it will be the cosine of 45 times the tension, and those are the components of the force that are pulling it forward. So I think the forces were like 1,200 newtons. I'm pulling that out of my head somewhere. So if you did the cosine of 45 times 1,200, then you would get the component. Now there's two of them, remember, there's two ropes. So this component pulling it forward, and this component pulling it forward, and when you add them boys up, that would give you the net force that's pulling the chandelier forward. Net force, then if you multiply it by how far it moves, that would give you the work done on the chandelier. Or maybe they give you the work and you multiply it by the force to find out how far it moves. I can't remember. Can't remember which problem that asked. But either way, that's kind of how you do it, because it was a confusing problem the way it was written. It's like, yeah, parallel to the surface, and it's 45 degrees from, I got kind of confused the first time I read it until I figured out what they were asking. So hopefully that helps you out. This slide said the total or net work, what I just explained, is defined as the work done by all the forces acting on the object, all the forces together acting on the object, or the sum of all the quantities of work. So you could do this. You could find out, well, how much work is done that way? Force times displacement. How much work is done that way? Force times displacement. And subtract those. Either way is right. I like just adding up all the forces because we've done that before, acting parallel to the displacement and multiplying it by the displacement to get net work. So you were supposed to work on those problems yesterday and today. That was the even numbered problems. If you want to shoot me an email or something with some answers, I'll be glad to check those. But if you want to try a few of the odd ones, you can, and I'll certainly check those. But hopefully this little lesson on work helps a lot with those two. I will try to do the next lesson by video. The next lesson should be the work kinetic energy theorem. That relates the amount of net work done on an object to the change in kinetic energy. Kinetic energy, energy of motion. So if an object speeds up or slows down, if it changes kinetic energy, then there's got to be some net work that causes that. There has to be a net force acting through a displacement to speed something up, slow it down, or possibly change its direction. We've said numerous times that objects are not going to speed up, slow down, or change direction without a force acting on them. So if there's a force acting through a displacement, then that's work. So really, work is kind of what bridges force and energy together, or at least changes in energy. So I told you before we left class that work and energy is one of those chapters that's really hard. You can see displacements, you can draw forces on a free body diagram. It's kind of hard to see energy changes and what's going on with energy. That's why I didn't give you a whole lot of problems on energy in my distance learning, but it's kind of difficult. So I'm gonna shoot you another video. I'm gonna link this to YouTube. I'll put a link on my website under links, so you can see the next videos on working energy. Hope this helped out, guys. I hope that that you're staying safe, that you are not out there doing crazy things with a whole bunch of people, because we want you to be safe. We want your families to be safe, and we want to see you back at school whenever that happens. So appreciate you listening, and we will see you soon.